Good evening. Well, who knows when you're actually watching this video, but for me it's evening. It's 11:15 p.m. on a Friday night. So I figured, I'm pretty tired, but you know what? I owe it to my students to get lesson 5.4 posted. So I thought, let me do that. So, lesson 5.4. Now, what I'm doing in this lesson, we're going to talk about applications of quadratics. And in this case, we're going to be solving because we've kind of done application of quadratics, just that was in Unit 4 when we were writing. Now we're solving these things. So it's going to be looking a little bit different. So this first page here are just some general things to think about when you are reading word problems. Whenever you're reading these real-world contexts, how should you be thinking about them? What should our approach be? Then I'm going to go through a few examples. I've got a couple examples on projectile motion, which is when an object flies through the air. And then I have another couple examples on area problems. In part 2 of the video, I'm going to talk about systems of a linear and quadratic, and maybe we'll do 1 or 2 examples there. But that'll be part 2. Okay, so let's talk about the main features of these things. So in yellow here, in my little laser pointer, I say finding the maximum or minimum of a parabola, right? So the useful thing about parabolas is when I graph them. Oh, sorry. I hope this doesn't start a chain of yawning. Sorry. Unless I got my parabola. Vertex is the height, right? It's the highest point. It could also be the lowest point, right? Maybe I make a bridge like this, right? And I have a little bridge. Then that would be the lowest point on those cables, right, for the bridge. So anyway, a lot of times problems are going to ask me for a maximum or minimum value in the context of that problem. So those are words you're looking for, max and min, and that refers to the vertex. So think about the strategies we've used to find the vertex, right? And we've got a couple things here. The main thing we've been practicing is putting standard form into vertex form by completing the square. We did that in 4.4, and then we did that, well, kind of again now, except more or less for solving. Now, I am going to introduce a little bit of a new thing in this video that I don't think we've talked about yet, and that is using x equals negative b over 2a. And we're going to use this to find the x-coordinate of the vertex. I'm going to explain that a little bit more when we get to it, but all that really is this is a, yawning. This is a small formula to figure out the x-coordinate of the vertex. It works every time. And I have an extra credit assignment where you can explore how to find this. Hint, it comes from completing the square. It also comes from taking the derivative using calculus, but that is for another time. So we can use this to find the x-coordinate and then easily find the y value that corresponds. That'll help us find the vertex. We'll also talk about calculator techniques on how to graph this in the TI-84 and then find the max or min and go from there. It's pretty simple, actually. Next is finding roots. And this is more or less review, right? I'm really just recapping what we've done in class. When I want to find the roots of a parabola, I'm looking for the x-intercepts. So I always set the equation equal to 0. Because where do those x-intercepts occur, right? They occur when y is 0. So if I have a function, right, y equals ax squared plus bx plus c, I want the y value to equal 0. So that's why I set it equal to 0. If it's factorable, and usually, if you've been practicing your factoring skills, you'll somewhat easily be able to notice when it is factorable. It's something I would always try, unless, of course, the numbers look a little too big, or if they just look Oh, goodness me. I'm so sleepy. Or if it just doesn't look factorable. But if you can factor, this quickly identifies the roots, and that's nice. If it's not factorable, well, we got two things we've talked about: quadratic formula and completing the square. We could do either one of those. And then the last technique is what we'll also talk about in this video, is we'll use a calculator to graph and identify those x-intercepts. It'll be pretty quick. I'm going to show you these techniques for graphing calculator for two reasons. One, to check your answers, right? To have another resource to verify that you've got the correct answer. Two, to have calculator skills that you might want to know for an SAT or an AP calculus, standardized test kind of thing. And I know, I mention standardized tests all the time. I'm not trying to I'm not just preparing you for standardized tests, but that is part of what we do in school. So better to prepare you than to not, right? So I try to give you these to use. Okay, and then last thing here before we start solving problems is a general, oh my goodness, yawn. And then, you say the word yawn and then you start yawning. You're probably yawning right now because I keep saying the word yawn. All right. So if I look at the features of a parabola, these are kind of the three main features you'll be looking for. Vertex for maximums or minimums. Root solutions / zeros for x-intercepts, which are like for a projectile motion problem. That's where something's going to land on the ground, right? So that would be that. The y-intercept is... Sometimes you'll be asked, at what point was this object released, right? Like how high above the ground was it thrown initially? Then that might be the y-intercept of your parabola. But who knows? It also depends on where you place your origin, because maybe, we've talked about placing your origin at the vertex, and in that case, the y-intercept would not be a starting point, right? But hey, who knows? Okay, so let's move on. Sorry, I tried to get a big one out so that I stopped doing this. I guess this is a bad idea to start recording so late. Oh, well. It's already been 7 minutes? Oh, my goodness. I gotta pick this up. I'm going to talk for too long. Okay. Projectile motion. So let me try and explain this real quick. Here is the equation for projectile motion. This is an equation we can use in physics. It models the height of an object above the ground with regard to time. Although this is, I will say the condition on this is we consider this in a vacuum, right? Where there's either negligible or no, right? No resistance of any sort, no other factors affecting this. This is how it would happen in a vacuum. And what do I mean by vacuum? Well, Google that. I'm not want to explain that right now. So to explain this equation, h of t stands for height, depending on time. And now I've got three constants here. I've got g, v naught, and h naught. When I say naught, I'm saying like v naught. That's how you'd spell that, all right? Which means v0. You could also call this v sub 0, right? V sub 0 is another way to say it. So yeah. Anyway, g is Earth's gravitational acceleration constant. That is what g is. It's on Earth, gravity is always going to pull us down at the same speed. Well, not the same speed, the same rate of speed. Sorry, I don't want to get too much into the definition of acceleration, but acceleration is the speed of speed, right? It's how fast you gain speed. So the idea of Earth's constant gravitational acceleration is if I were in a vacuum and I dropped a feather and was it an anchor? I don't know. They would fall at the same rate. They would gain the same momentum, the same speed, and hit the ground at the exact same time. There's actually a wonderful video on YouTube for this. You should look it up. It's great. But that's the idea of G. So it's always going to affect it. It's a fixed thing determined by our Earth. All right. Now, if we were on a different planet, the value of that gravitational acceleration would change. But because we're on Earth and because we're throwing stuff on Earth, it's always going to be that. V naught is initial vertical velocity. I notice now I have a little typo that says initial. This is supposed to say initial. There we go. Initial vertical velocity, meaning how fast is it going up or down the instant it's launched, right? The instant it is released from your hand or from some propellant of some sort, that's what V naught is. And then lastly, H naught is your initial height, meaning how high above the ground did it start at, right? That's what those things mean. And typically, just so you know, in math, like A sub 0, A naught, that little naught that we use usually indicates initial. So it's kind of a takeaway there, if you didn't know. Okay, it's been 10 minutes. Mr. Spade, can you finally work an example? Sure, absolutely. Let's do one. Okay. So let's look at example 1. An object is dropped from an initial height of 90 meters. Question A. Write a formula describing the height of the object in meters after t seconds. Okay. So this sentence, I know it doesn't seem like a lot because it's a very tiny sentence. An object is dropped from an initial height of 90 meters. But this tells us 3 pieces of information right off the bat. Just right off the bat. First thing is G. Notice my problem is in meters. So I know that G is right here. So if G is in meters, G equals negative 9.8 meters per second squared. So I'm going to say negative 9.8 meters per second squared. Next, so now I have V naught and H naught. H naught being the initial height, well, it tells us exactly that the initial height is 90 meters. Whoa. Oh, 90 meters. And the initial height, the initial height is 90 meters. The initial velocity, well, what is that? Well, it says the object was dropped. So when we talk about initial vertical velocity, it's how fast is it moving the instant it's released or propelled. Well, if I drop something, I'm not applying any force to it, right? I'm not throwing it up, I'm not throwing it down, I'm dropping it, which means it's starting at a speed of 0, right? So it's going to be a velocity of 0 meters per second. Okay. Oh, and by the way, I don't think I said this. This equation, h of t, blah, 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 you don't need to memorize that, okay? I'm not going to require that you memorize that. But what's important is that these 3 things, you need to be able to identify those in that formula, okay? Or equation, whatever you want to call it. You need to be able to identify those pieces. So, okay, so if I write this, h of t equals 1/2 gt squared. Well, g is negative 9.8, so this is going to be negative 4.9 t squared plus 0t, because v naught is 0, right? V naught is 0, so that's 0t. And then the initial height was 90 meters. So I got it. Box my answer. I'm getting really sleepy. All right, so that is the height of the object. All right, let's move on. Part B, after how many seconds does the object hit the ground? So that's our goal. We want to figure out when this thing hits the ground. So what we're looking for is the x-intercept, right? looking for the x-intercept, or in other words, the roots, right? So I say, when does h of t equal 0? That's like saying, so I like this. Oh, I didn't do this in class? Oh, missed opportunity, Mr. Spake. I really should have done this in class. This is a beautiful time to do this. Well, at least we'll get it here in the video. So if I set h of t equal to 0, then I get negative 4.9 t squared plus 90 equals 0. We don't need to use the quadratic formula on this because there's no t term. So we could just solve for t by taking the square root. So if I subtract 90 from both sides, I get negative 4.9 t squared equals negative 90. And I'll divide by negative 4.9 on both sides, getting me t squared equals, I have no idea what negative 90 divided by negative 4.9 is. 90 divided by 4.9. Okay, that's an ugly number. I want to try that again. Is that right? 90 divided by 4.9. Yep, okay. It's 18.3673. And there's more decimals, but whatever. I'm just going to round it to that. Okay? Now, to figure out t, I got to take the square root. Take the square root. Say plus or minus, right? But obviously, because it's time, you see, when I take the plus or minus root of that, do I really care about the negative result? No. So I might even write that. Time can't be negative. All right? It's not going to be negative. Now, I mean, I guess there's certain contexts where we could use negative time to refer to time before a particular event, if we call that event time equals 0. But in general, we're not going to use negative time. All right? So what this means is, so this tells me t equals the positive square root of 18.3673. And so I say, therefore, t equals. Now I do believe isn't this a nice number? Let's take a look. I'm going to go to my calculator. Now, so if I do square root of 18.3, hold on, 0.36. Oh my God, I can't type. Yeah. And then I just want to double type. Sorry, I'm fiddling around on my calculator on my phone here. You can't really see it. Okay, cool. My approximation is pretty darn accurate, so I'm going to stick with it. T equals, I'm going to round to 3 decimals, 4.286 seconds. Done. All right. And there you go. Okay? Awesome. Okay. Does the next question do this? Okay, cool. Yeah, it does. So I'll talk about calculator methods on the next one. But there you go, right? That one was just a simple take the square root of it and you are done. Beautiful. Absolutely wonderful. Let's move on to example 2. Example 2. So, I made up this problem based off just me and my friends' recent gameplay in Call of Duty. So Mr. Spake's friend Carmine is not very good at Call of Duty. I tell you, he used to be. Modern Warfare 2009, guy was a legend. But I don't know. I guess our older age is starting to get to us. At the time of filming this video, I am 25, so I'm really not that old, but still, I don't know. Mr. Spake at the age of 16, oof, Now, that's a guy you didn't want to be in a lobby with. Okay, sorry, I'll shut up. So, after losing 5 S&D matches in a row, Carmine throws his controller in a fit of rage out of the second floor window of his apartment. So the window is 24 feet above the ground, and he throws this controller with an initial vertical velocity of 20 feet per second. So I think that's pretty darn fast, right? I mean, this guy's mad, right? Carmine is not happy. So let's write the equation, right? What is the equation? Well, it's going to be h of t equals, so I have to label these pieces, right? G is going to be negative 32 feet per second squared. And if you're wondering, where did Mr. Spake come up with this? It's because Mr. Spake knows that if I have a problem in terms of feet, G is negative 32 feet per second squared. And this problem is in terms of feet, so it's that. You don't have to memorize that. The problem would give that to you, okay? Or I would give that to you on the test, so to figure out. V naught being the initial vertical velocity, it says it's 20 meters per second. And H naught is the height of the window. That's where the controller leaves the window. That's 24 feet. So my function is negative 16t squared plus 20t plus 24. And if you're asking where did that negative 16 come from, it's half of negative 32. Because that is the formula here, right? Half gt squared. Okay. So I've got 2 methods here that we could do. All right. Our original method of completing the square, if we complete the square on this function, we can put it into vertex form. And because you find the vertex from vertex form, that tells you the maximum height. So let's try this real quick. Mr. Spake is going to try and not make any mistakes here because he's very sleepy. Okay, so I'm going to take negative 16t squared. I'm going to zoom in right here. Plus 20t plus 24. Okay, and this is, I'm going to call this y equals. So y equals, I'm going to factor out negative 16 because I have to get the leading coefficient a equal to 1. And so that's like minus 20 over 16t plus 24. But then, of course, let's switch to yellow. Negative 20 over 16 is just negative 5/4. Yeah, okay, sorry. Yeah, it's negative 5/4. So take b over 2 squared. That's negative 5/4 over 2 squared. And you can use a calculator or whatever, okay? Or you can do it by hand. The result you should get is 25/64, I believe. Because this becomes, look, if I'll actually write it out. 5/4 over 2, that's negative 5/8 squared, which means that's 25 over 64, not 8. 64, because I square 5 and I square 8. And the negative's gone. Okay, so that's the magic number I'm adding. So y equals negative 16 times t squared minus, I'm going to reduce that to negative 5/4 t plus 25 over 64. And then plus 24. And I got to be careful here because what I've done is I've multiplied negative 16 multiplied with this. So I need to add 16 times 25 over 64. All right. Now this is just some math. This is just some arithmetic here. This is a perfect square trinomial. Okay, every time. Always a perfect square trinomial. So you can factor this pretty darn easy if you just know that you You can think of it two ways. Either it's half of that b term, because it's b over 2, or it's the square root of this, because that's still b over 2. So this is t minus 5/8 squared. That's how that's going to factor. Now, if you need to do a little factoring puzzle to figure that out, you're by all means go do that. But if you learn that kind of shortcut technique for factoring for perfect square trinomials, then you don't need to bother with that. And then plus 24 plus 16 over, oh, yikes. Is 16 times 4 64? Usually I would know this off the top of my head, but as mentioned, sleepy. Okay, yeah, so that is 4. So this is like plus 24 plus 25 fourths. That's what that is. Is that right? Again, I don't want to make any mistakes, so I'm not taking any. Oh. 25 fourths. 20. Yeah. Okay, cool. Sorry, hey guys, I'm just making sure. All right, I don't want to be teaching you the wrong thing. I know it extends the runtime of the video, and I'm sorry, but hey. Now I can get a common denominator here. 24 times 4 is 96. So this is like 96 fourths. And then this just means y equals negative 16 t minus 5/8 squared plus whatever the heck 96 plus 25 is 121. 121 over 4. So vertex is at 5/8, 121 over 4. Of course, 121 over 4, that's okay. And so if I were to put these as decimals, this would be 0.625, and this would be 30.25. All right? So I'm going to say the max height is 30.25 feet. And now, perhaps you're asking, Mr. Spake, why didn't you just write it as 121 over 4? And I say, well, who are you going to go to someone and tell them that this building is 121 feet divided by 4? Probably not. You might more likely say, oh, it's 30 feet, 0.25, right? It's 30.25 feet. A little bit more manageable that. Now, that wasn't the worst completing the square problem. That's actually really not that bad. It's a decent one. But there you go. That's finding the max height by completing the square. Now, method 2, this is the new method I want to show you. Okay, so there you go. You got your complete the square for method 1. Ta-da. Let's use method 2 now. Now, method 2, we could do a lot of stuff with hand calculations, or we can use our calculator, and it'll be really quick. So t equals negative b over 2a, and b is 20, so it's negative 20 over 2a. A is negative 16, so this is negative 32, which simplifies to 5/8. Ha! Look at that, right? T, so t equals 5/8, or I could say t equals 0.625 seconds, right? And that's the time on how long it takes to get to the maximum height. So if I plug this in, right, if I say if h of t, so I say h of t equals negative 16t squared plus 20t plus 24, then I say h of 5/8 Let me zoom in here. We don't need to be that far out now. H of 5/8 equals negative 16 5/8 squared plus 20 times 5/8 plus 24. You see, what we're doing here is, perhaps I should explain this since it's a new method. This formula for t, or x, tells you the x-coordinate of the vertex. So if you have the x-coordinate of the vertex and you substitute the x value into the function y, well, the function y, or in this case h of t, tells me the height of the object. So when I replace that time into the function h of t, this h of 5/8 is telling me the maximum height. And all this is computation. Now, I'd like to try this by hand because I like to do things like that. But let's see here. So 5 squared, that's 25. And then one of those 8s is going to cancel. So 25 times 8 is negative, I can't think, 200? Let's be sure. 25 times 8. Oh my God. 200, yeah, okay. Negative 200 plus, now 20, that's going to be like 4, was 20 over 8. Ooh, picked the wrong day for mental math, Mr. Spake. 5 times 5 is 25 over 2. So 25 over 2. This doesn't seem right. Hold on. I'm going to go to my Desmos calculator. Negative 16 times. I'm sorry. Hey guys, just scroll through the rest of the video. Unless you just want to hear me talk, right? Unless you truly just want to hear that. Oh, it's 4. Oh, dummy. The 6. It's not 4 times that. It's 25 over 4. Negative 25 over 4. Not negative 25 times 4, Mr. Spake. Plus, so 24 in terms of fourths. That's 24 plus 4. Oh gosh. 20 times 4. This is like 96 fourths. And that's like 50 halves. 50 fourths. All right. So this is 25 fourths plus 96 fourths, which equals 121 fourths. Ha-ha! Did it. Got it. Equals 30.25. Okay, look. Look, I did all that by hand. I'm not expecting you to do that, okay? Take your calculator. Just type it in. All right. Max height is 30.25 feet. Box that. And I'm going to write. I'm gonna write this. I did this for fun. I'm going to say just use your calc. Okay? I did this for fun. Just use your calc. You don't have to do all that, okay? All right. Wow. This video is going to be long. Okay. At what time does the controller hit the ground? So you see how I've done this problem twice with two different methods, but both ways I got the max height, right? Oh shoot! Before we move on, I gotta talk about how to use the calculator. So here's how to use the calculator, because that's what this is for, to show you new methods as well. So you can use either of these two methods, and you can use a calculator. So here's what I'm going to do. I'm going to go to my TI-84. I'm going to go to, let's clear this. I'm going to go to y equals, and I'm going to type in my equation. Negative 16x squared. Whoa. Is that the right x? Why is it doing a capital like that? I guess it's fine. Okay, negative 16x squared. Was it plus, what was it? 20? 20x plus 24. So I graph. Okay, and that's, I guess you can't really zoom. So, sorry. Okay, so see what I'm doing here is I'm pressing y equals. So I'm typing the equation, and then I click graph, and I don't see it here. So what I'm going to do is I'm going to click zoom. You see zoom right here. And then I'm going to scroll to option 0 here, which says zoom fit. And if I do that, I can see the parabola like so. Now, I'm looking for the maximum, right? I want to find the maximum of this parabola. So I'm going to click second, trace. This goes to calculate menu. And I want you to notice there's a whole bunch of different things here. There's value, there's 0, there's minimum, there's maximum, there's intersect, there's dy dx, and there's the integral of f of x. 6 and 7 are calculus things, but 1 through 5 are things we can use in algebra. We want the maximum of this parabola, so we will click maximum. Now what it's going to ask for is a left bound. Now I'm using my finger to, can you see that little dot? I hope you can. See the little dot moving around? I'm using my finger on my iPad to pick a left bound, meaning go a little bit to the left of the vertex. Once you do that, click enter. Then it's asking you for a right bound, and I'm going to go a little bit to the right of the vertex, not too far. And I'm going to click enter. And there you go. It estimated the point of the vertex. Oh, you can't see. Okay. I wish I could zoom in on this and show you. But if you look there, look carefully, you see how it says max x equals 0.625, y equals 30.25? That verifies the answer we got because we got those results. And that is the maximum. Okay? So that's how you can check that with a calculator. Again, the steps were y equals, graph it. We wanted to fit it to our windows, so we clicked zoom fit. And then we did second calc, maximum. And then you choose a left bound and a right bound just by clicking enter. Right? Enter, and then double enter, and then there you go. Finds the maximum. Okay? All right. So let's move on to part B. And honestly, I think I said I was going to do the area problems in this video, but I think I got to call it, guys. I'm too sleepy. I'm just, you don't want me rushing through these last two. Okay? So I'll just make a part 2. All right. At what time does the controller hit the ground? Now, when does it hit the ground? We're looking for zeros, right? Let me see here. When I say max height, that implies vertex. And when I say hit the ground, that implies roots / x-intercepts. So I'm looking to when does y equals 0, right? So I can do this by factoring. I can say y equals negative 16. Actually, remember, whenever you're finding the zeros, you set it equal to 0, right? So negative 16t squared plus 20t plus 24 equals 0. Now, all of these are divisible by 4. So if I divide by 4, then I get negative 4t squared plus 5t plus 6 equals 0. By the way, I'm allowed to divide by 4 because what I'm doing is solving an equation. You can't divide by 4 if you're just manipulating an expression because you have to keep it the same expression. But in this case, the equation will remain balanced by division through 4. And from here, could I just do guess and check? No, I'll do factor by grouping. If I want to do factor by grouping, I'm going to factor out the negative because I have to have that negative factored out. Okay, I gotta if I'm going to do factoring. So I say cross puzzle, 4 times negative 6 is negative 24. Down here's negative 5. Whew, what works? 6 and 4, no. 8 and 3. 8 and 3, so 8 is negative, and there's 3. So say negative 4. Actually, so here's the thing. You don't even need the negative anymore. Let's say I divide by negative 1. Then I got 4t squared minus 5t minus 6 equals 0. And now that just gets rid of that negative business, okay? And so this is now 4t squared minus 8t plus 3t minus 6 equals 0. So I'll do 4t times t minus 2 plus 3 times t minus 2 equals 0. So then this factors as t minus 2 and 4t plus 3 equals 0. So then, I see, so then either t minus 2 equals 0 or 4t plus 3 equals 0, because I want to figure out, right, zero product property. I want to figure out what makes this go, which makes these factors go to 0. Here I just add 2. And then here I'm going to subtract 3 from both sides to get 4t equals negative 3 and divide by 4, getting me t equals negative 3/4. Except I don't want that because time not negative, right? T is not going to be negative 3/4. So I'm going to finalize it by saying, therefore, t equals 2 seconds. Ooh, that was terrible. Hold on. Sorry. T equals 2 seconds. Box it. All right, whatever. It'll just have to fit in there. Okay? Okay. Let's do our last method. Okay. So you see that it was totally done by just factoring. So that factoring by grouping had use. Okay? We got this problem's designed to be doable by hand though. So that's why the numbers work out. If the numbers aren't, so see what I'm doing in red here, these are those sort of more abstract theoretical problems we've done where the numbers work out because they're kind of pretty. But what I'm doing in blue here is more, these second methods are actually what you probably would want to do when the numbers don't look pretty. All right, when the numbers look ugly, don't do completing the square, don't do factoring. It's either not going to work out or it's going to be way too complicated. These are going to be more straightforward because they use formulas. Now, of course, these formulas come from doing the abstract thinking, but yeah. So if I say t equals negative b plus or minus the square root of b squared minus 4. A was what? Negative 16. 4ac all over 2a. There you go. There's your little song. There's your little song of the day, all right? Now, if I calculate this, I get 2 results, okay? And this is, I'm gonna I'm gonna write this in yellow so that it's on the notes. Plug into calc. All right? That's all you got to do. You plug this into a calculator. So I'm not going to pull open Desmos and do that on my iPad because I don't want to go back and forth and look. So I'm going to just use Desmos on my, okay, so it's a negative 20. Okay, you know what? Hold on. Let me show you something. Because you want to use the graphing calculators, right? Get away from Desmos. Alpha frac. Oh, that didn't work. Alpha frac. There it is. That makes your fraction. So it's negative 20 plus second square root 20 squared minus 4 times a was negative 16 times c was 24 all over, come here you, hello, the heck, okay, I wasn't working, I wasn't responding, all over 2 times negative 16, enter, wow, look at that, I get negative 0.75 by doing the plus. So if I go here, I get t equals negative 0.75 or t equals, and I'll go back to the calculator, and in that equation, can I copy it? Okay, copy down the equation, but it's plus or minus, so let's delete the minus and delete the plus and put a minus, calculate, I get positive 2. So, again, reject because time not negative. And so, therefore, t equals 2 seconds. All right. And there you have it. Wasn't that beautiful? Wasn't that just great? All right. So, not a whole lot new in terms of solving. I mean, the red stuff is just stuff we've been doing, but at least you kind of get to see it thrown into a real-world context. Again, the blue is probably what you want to stick with on the multiple choice section of the exam. Know your quadratic formula. Know how to find the vertex with this little formula for the x-coordinate. And that's going to help you out a lot with those calculations. Okay? All right. I think I need to end part 1 here because I think I'm getting it right about to the hour mark, which is kind of insane. I'm sorry for taking this long. It's really bad of me. I should not have taken this long to do this, but I'm slow tonight. So I'll get part 2 up soon. Enjoy the rest of your day. I hope you enjoyed this video. I hope it wasn't too slow, but I hope you found it useful and beneficial. So I'll see you around.